A 0.4 kilogram ball is launched horizontally with a velocity of 30 meters per second from the top of an 80-meter high building, and the potential energy of the ball is 0 at the bottom of the building. So that's giving you your arbitrary reference point. Part A, let's calculate the potential, kinetic, and total mechanical energies of the ball at time t equals 0 when it is launched. So, potential energy, it's gravitational energy. So we're going to use mgh and just plug in 0.4 times 10 times the height of 80, for which you'll get an answer of 320 joules. Then kinetic energy is 1/2 mv squared. So that'll be 1/2 times 0.4 times the initial velocity when it's first launched, which is 30 squared. Remember, the energy is a scalar, so we don't have to worry anything about directions. We just take the total amounts. And when it's first launched, it's launched at 30 meters per second. And this gives you an answer of 180 joules. So that means the total mechanical energy, which is kinetic plus potential, 320 plus 180, you get 500 joules. So now we're going to represent this graphically two different ways. The first is energy versus distance fallen, and the second as mg versus time. So for energy versus distance fallen, let's go ahead and plot the points that we know. So at time t equals 0, when it hasn't fallen any distance, the initial gravitational energy is 320. So I'll put a dot around 320. The initial kinetic energy is 180. So I'll put a dot there for kinetic. And the initial total mechanical energy is 500. So we'll put the dot right there. Now, since there are no non-conservative forces acting in this problem, because the object's in free fall and the only force acting on it is gravity, that means the total mechanical energy will be conserved. So because the total mechanical energy is 500 initially, it's just going to stay at 500 for the full 80 meters that the object's falling. So you should just have a horizontal line on the graph at 500. And we'll label that line as E, the total mechanical energy. Now let's look at the potential energy, the gravitational potential energy. And for that one, you'll notice that the potential energy, the U, is directly proportional to the H, which is the height above the ground. So as the object's falling, when it gets to the ground, after it's fallen 80 meters, since it's the ground level, the potential energy will be 0. So on this graph, we're going to put a dot at 80 meters and 0 joules of energy. And because it's a linearly proportional relationship between the U and the H, or the U and the distance fallen, we can just write this as a straight line going from 320 down to the 80. Let me redo that to make it a little better. One more time. Well, screw it. It's supposed to be a straight line. And at the same time, the kinetic energy has to increase. Since the potential energy is going down, the kinetic energy has to go up, so that the two of them added together will give you that total energy line. So when it has hit the ground, the kinetic energy will have to be 500 joules. So at the 80 meter mark, we can put a dot at 500 joules, because all of that kinetic energy, all of that total energy will be kinetic, and none of it will be gravitational energy. And that graph is just going to increase at a linear rate, since the other graph decreased at a linear rate. So you should just have a straight line going from 180 up to the 500. And remember, just make sure that all of your lines are labeled. So we need to put that a K for that line, and we need to put the U, the potential energy, on the other line. Okay, now let's draw a graph of potential kinetic and mechanical energies as functions of time instead of as functions of distance. One final thing to note about part B before we move on to part C is that if you look at this equation, you say, well, how does that relate to having a straight line? Well, this is where kinematics comes in, because kinetic energy depends on v squared, and from kinematics, v squared is equal to VO squared plus 2AD. So in the vertical direction, the initial velocity is 0, since it was launched horizontally. And what this shows you is that the v squared is actually proportional to the distance. So since kinetic energy is proportional to v squared, and v squared is proportional to the distance, that means kinetic energy is directly proportional to the distance. That's a linear relationship between K and D, which is why that graph forms a straight line. Okay, so on to part C. Let's draw graphs of those three energies versus time. First thing is we have to figure out is how much time does it take the object to reach the ground. So because we're looking at time, that doesn't show up in any of the energy equations, so we're going to have to use kinematics. So using kinematics, we're going to say that in the vertical direction, because that's what determines the time, the initial velocity is equal to 0. Let's define downward as the positive direction, since the object has no upward motion. So the acceleration is positive 10. The delta y, the vertical displacement of the object, it goes down by 80 meters, and since downward is the positive direction, that's going to be a positive 80 meters, and we are looking for the time. So t is our question mark. We're going to pick the kinematics equation that is missing the final velocity, which is delta y equals VOT plus 1/2 AT squared, and since the initial velocity in the y direction is 0, I can get rid of that from the equation, and then I can rearrange what's left to get the t by itself. So t is equal to 2 delta y over a, and take the square root of that whole thing. Plugging in the numbers, that gives you 2 times 80, that's 160, divided by 10, that gives you 16. The square root of 16 is 4 seconds. So that tells you that the object lands at 4 seconds, and since the graph goes up to 8 seconds, that means all of this part of the graph over here should not be filled in at all. Just leave it totally blank, and only fill in that part of the graph up to the 4 seconds. So, first part's easy. For the total energy, because that's exactly the same as before, we know the total energy to start with was 500 joules, and we know the total energy when it lands after 4 seconds is also 500 joules, so that part of the graph stays the same. And we also know that when it was first launched, the potential energy was 320, and the kinetic energy was 180. And we also know that when it lands, the potential energy was 0, so we can put the dot down there, and the kinetic energy was 500, because all the energy, all that mechanical energy is kinetic at that point. The one difference, though, is that these are not going to be linear relationships this time, because if you look at the equations were linear functions when it was referring to distance. Like u was directly proportional to distance, which is linear. K, the kinetic energy, was directly proportional to this distance, so that's linear. But now we have to look at how the u and the k are related to time using the kinematics equations. So if we look at, let's take the kinetic energy equation for example. K is proportional to v squared. The equation that shows the connection between v and time is that first kinematics equation. It's the one that says v equals VO plus AT. So in the vertical direction, with the initial velocity of 0, the k of the v is proportional to the t. which means if I squared this, we'd have v squared is proportional. That little fish symbol means proportional. V squared is proportional to t squared, since v was proportional to t. So k, being proportional to v squared, is now proportional to t squared. So that's going to be a curved graph. Let's look at it also with the gravitational energy. The gravitational energy, U, is proportional to mgh. Remember, h is the height above the ground, which we can also think of that as if we're looking at it upside down, or if h is the height above the ground, it also is linear with the distance fallen, as shown in the previous graph. And we know that the distance fallen is delta y is equal to VOT plus 1/2 AT squared. I'm leaving out the VOT, since the initial velocity vertically is 0, but you can see right here that the U, which is directly proportional to h, or the distance is proportional to a t squared. What that means is now that both kinetic energy is proportional to t squared and potential energy is proportional to t squared. So for the potential energy, let's go ahead and do this graph first. That's the blue one. We have a curve that moves, so it kind of goes more steep as it goes on. As the time is increasing, the delta y, the distance, gets exponentially bigger. And then the same thing with the kinetic energy. This is just going in the negative direction. So that graph will look something like this. So that when the numbers on the two graphs are added together at any point, the two numbers should add up to 500 for the total energy. For example, let's say roughly 3 seconds, it looks like this graph is around 200. If it was perfectly drawn, this blue graph would be around 300, and the 200 plus the 300 would give you that 500.